Take an average person from the early 1800s and put him into a time machine. Now imagine that your goal is to maximize this person's dazzlement by sending him to an era utterly alien to his own, but you have only two choices. You can either send him 200 years into the future or 2,000 years into the past. Which would you choose? Which age would be the more baffling to him? That of his descendants some 8 generations on, or that of his ancestors 80 generations back? In the event that our early 1800s time traveler were sent back to arrive, let's say among the ancient Romans around 200 BC, he would encounter a set of somewhat unfamiliar customs and contrivances, and he would certainly notice many things missing that had defined his own daily life, from guns to glass for windows and spectacles. Yet the fundamentals of daily life, how people communicated with one another and entertained themselves, their level of comfort, all would be pretty close to his own experience. It wouldn't take long for our early 1800s man to settle into the world of even his ancient ancestors. Arriving in the early 21st century, on the other hand, he would probably assume he had stumbled into some kind of wizard's dream. Just a single smartphone would be so mysterious, so contradictory to his sense of what was even possible, that he might appear hopelessly incapable of rational comprehension. As an ambassador of the modern age, how might you enlighten him? Presented with a smartphone, the man from the past would ask dozens of questions. Where does the light come from? Is this thing alive? How are you talking to someone someplace else? And on and on. Listening to his questions, you might realize that they all seem to point toward the same underlying concept, a principal technology from which the phone and most other modern technologies derive. The more you talked with our time traveler, the more you would see that the prime mover of modern life is electricity. Most of what would make our world so bizarre to this man, after all, is energized by electricity. Everything from the smartphone to food refrigeration. Electricity would represent the real alchemy of his wizard's dream. If he understood its history, maybe the smartphone wouldn't seem so impossible to him after all. Let's tell him of electricity then, and how it began. The bell towers of London, England signal midday over the bustling city. Smells of manure, smoke, and unwashed bodies crowd the air. The year is 1600, and the city's population has been doubling every couple of generations since the Black Death 250 years earlier. Some 25,000 souls were left in the wake of that great plague. There are over 200,000 Londoners now. A brilliant natural philosopher named William Gilbert is among them. Bathed in sunlight as he sits at his desk alongside his apartment's only large window, he pauses in his writing for a moment to listen to the church bells reverberate off the stacked rooftops nearby. He feels he can afford to set his quill pen down now for an extended moment of reflection, to bask in the imminent completion of a great work that has taxed his mind for years. He is 56 years old. Throughout his long life, he's been fascinated with the subjects of his new book, magnets and sparks and lightning, and he'd grown obsessed with understanding their invisible power. 2,000 long days of experimentation and reasoning, writing and rewriting on the subjects now stretch behind him. all that's left on this day is to write the title and some dedications, and his manuscript will be off to the publisher. Before the sunlight drifts into shadow behind a nearby steeple, Gilbert picks his quill back up, dips it, and turns a fresh leaf of paper. In bold ink, and in Latin, of course, he writes his title. On the magnet and magnetic bodies, and on that great magnet, the Earth. Despite the focus of the title, the manuscript deals deeply with electricity, and among its incredible revelations on how magnets and compasses work, Gilbert also establishes therein the idea of an electric force, using the word electricity as we now understand it for the first time in history. Through disciplined observation and experimentation, William Gilbert swept away dozens of thousand-year-old superstitions about electricity and magnetism, cleaning the slate of these otherwise occult subjects and inspiring generations of natural philosophers to rationally investigate the phenomena. And although Gilbert got several things wrong about electricity and its relationship to magnetism, he gave the scientific community an excellent head start on the topic, inventing the first practical instrument for measuring electric charge and correctly reasoning that the Earth itself was an enormous magnet. Building upon Gilbert's rational conception of electricity and its apparent relation to magnetism, investigators went on to construct ever more elaborate experiments to tease out its power. The well-known phenomenon of static electricity was where most began. Children's hair standing on end after they'd donned a wool frock, or small sparks that jumped from metal doorknobs to fingertips on a dry winter day, had long been perceived by most people as simply the more benign glimpses of God's power, which could mount to terrifying degrees in the form of a lightning bolt should his wrath grow sufficient. But by the beginning of the 1700s, after a century of carrying on with the legacy of William Gilbert's work, clever experimentalists had succeeded in building machines to summon shocks at will. These featured basketball-sized metallic or glass orbs connected to crankshafts that could be rotated at high speeds, against which anything from a silk handkerchief to a metal comb was applied to generate a charge. The principle was straightforward enough. It seemed obvious that the friction between certain materials produced the sparks, so the rotating sphere model was a simple expedient. In 1705, the man in charge of demonstrations at the Royal Society of London, named Francis Hauksbee, built the most effective such model, and it was used by dozens of researchers from then on to make new discoveries. In 1720, for example, a fellow Englishman named Stephen Gray used a Hauksbee machine to demonstrate how an electric charge could flow like a liquid through certain substances rather easily, such as metal and even a human being, and how it could be contained by others, such as glass and silk. He called these material sets conductors and insulators. Through this phase of experimentation, scientists developed both a basic familiarity with electricity's behavior and the engineering skills to manufacture electrical equipment that was necessary for more advanced study. The invention of simple metal wire, for example, proved to be a major breakthrough in itself, opening up vast new experimental avenues that relied on precise electrical conduction. Overall, through the first half of the 1700s, investigators made great progress in generating, conducting, insulating, and measuring electric charge, rendering the study of electricity itself a more practical and thereby more attractive field. So even though no one had any idea what electricity actually was, the fact that it could now be summoned and channeled at will helped to ensure steady scientific progress. And by the 1740s, the leading edge of research was focused on how to actually store an electric charge. The prevailing theory that electricity was some kind of fluid proved particularly useful. In 1745, a Dutch professor in the town of Leyden in Holland named Muschenbroek sought to store an electric charge in much the same way that one might go about storing water, by pouring it into a glass jar. Muschenbroek began working on the problem soon after he got his hands on the new experimental equipment of copper wire and a Hawk-speed generator, and his experiment was quite simple. He just ran some insulated copper wire from his generator to a brass knob on the top of a cork-sealed glass jar, and from there down into the jar itself, where it was submerged into a few inches of water that the jar contained. His idea was that the electric fluid generated by cranking a Hawksby machine would flow right into the water through the wire, where it would remain stored, fluids suffused, until someone discharged it by touching the brass knob on the jar's lid. Through trial and error, Muschenbroek succeeded, accidentally shocking himself in the process with the largest electric charge anyone had ever experienced, aside from suffering a lightning strike. But there was something strange about the particular procedure needed for success. His jar appeared to store up electricity only when he held it in his hand or provided some other equivalent kind of conducting conduit to the ground while charging it. His device, which became known as the Leyden Jar, was a sensation throughout the scientific community, and when news of it arrived on the other side of the Atlantic Ocean, one of the brightest minds of the American colonies became fixated on that peculiar necessity of grounding the jar to charge it. When it comes to electricity, Benjamin Franklin is most famous for his alleged experiments with lightning, but ironically, he probably never actually performed them himself, and almost certainly did not attempt to fly a kite in the middle of a lightning storm. He was too smart for that. These were more like thought experiments to help him reason through electrical theories. And one thought experiment that he proposed for explaining why the Leyden jar needed to be grounded during charging resonated so well that it permanently affected how we talk about electricity and magnetism. Franklin, as a man of the Enlightenment, interpreted electric charge in the same way he idealized politics and the economy, as a balance of opposing forces, and he proposed that a shock merely represented the abrupt balancing of unequal charges. Franklin reasoned that when Muschenbroek cranked his generator to send electric charge flowing into the Leyden jar, there had to be some source for an equally opposing charge to collect against the outside of the jar's insulating glass. Without that source, no matter how vigorously Muschenbroek cranked, he could not force nature into such imbalance, and the electric fluid would not flow into the jar. For Franklin, electric charge was like financial accounting, and nature always wanted to balance its positive and negative transactions. For a surplus of electric charge to collect in the Leyden jar, then, an equivalent deficit of electric charge had to be available to build up right alongside it, just outside the glass. Holding the jar while standing on the ground or attaching conducting wires to it that ran to the ground allowed for such a balance. The balancing deficit of electric charge could be drawn up directly from the Earth's vast reservoir. This, Franklin reasoned, was why Muschenbroek only succeeded in charging the Leyden jar when he held it. And this successful analogy permanently imbued the language of positive and negative charge into the discourse on electricity. Over the next half-century, electricity continued to be all the rage among scientists. From lightning to electric eels, investigators tackled its numerous sources to establish ever firmer theoretical ground upon which the once supernatural-seeming force could be rationally understood. Through the 1770s, experiments comparing the charges given off by Leyden jars and stingrays captured off the west coast of Africa revealed that the strength of electricity manifested in two distinct ways: through its amount, or current, and its intensity, or what would soon be called its voltage. The useful analogy once again being as a fluid, imagined as the total volume of water flowing and how rapidly it flowed. An English researcher named Henry Cavendish theorized that the same discharge of electric power could either kill a man or be completely benign depending on these values, just like a man who might drown in a sudden rush of whitewater rapids could swim comfortably in that same amount of water if it flowed as a lazy river. Intrigued by the fact that certain animals like eels and stingrays could emit an electric charge seemingly without moving, and motivated by professional rivalry to prove that animal electricity was the same as any other kind of electricity, an Italian chemist named Alessandro Volta sought to build a device that would produce an electric charge without any moving parts. As a chemist, he believed that the most obvious way to do this was to induce some kind of chemical process to move electric current in place of the mechanical process of cranking the glass sphere of a Hawksby machine. Given that metals were known to be good conductors, Volta played around with an assortment of metal for months, at one point apparently tasting their various combinations. This is not so strange as it may sound. Natural philosophers were in the habit of using every one of their senses to explore the world. When he was rolling a couple of coins around in his mouth one day, one made of copper and the other of zinc, he noticed a unique taste only when the coins were on opposite sides of his tongue. It was an extremely subtle, buzzing kind of taste, but it was definitely there and only there when the coins were on opposite sides of his tongue. He replicated this by stacking a series of copper and zinc discs together, separated by salt water-soaked paper, and after refining this design and strengthening the effect by replacing the salt water with acid, he succeeded in building a powerful chemical battery. His colleagues dubbed it the Voltaic Pile. The most important thing about the Voltaic Pile, the thing that made it a powerful force for world change, was not so much that it produced electricity through chemical action, however novel that might have been, but that the electricity it yielded flowed in a continuous current. The Hawksby machine, by contrast, produced only instantaneous bursts. Volta's pile did nothing to help scientists understand any better what electricity was, but by unleashing a continuous current, it revolutionized the manner in which researchers could investigate it, and even more profoundly, continuous current appeared to offer practical applications for electricity for the first time. Unless our time traveler made a habit of reading academic journals or attending Royal Society lectures, he never would have known that a revolutionary battery existed in his own time. It took almost a decade of additional research before anyone publicly demonstrated the battery's vast potential. In 1808, the English chemist Humphrey Davy wired together an entire room full of voltaic batteries to produce an electric current so strong that it arced several inches across a gap into electrodes in a blindingly bright and continuous spark. In a world lit by the soft flames of hearth fires, candles, and oil lamps, Davy's arc light strikingly illuminated the possibility of a much brighter future. Another decade on, and even more tantalizing electrical effects were observed using the continuous current of batteries. In 1820, a Danish physicist named Hans Christian Ørsted found that when he moved a battery-charged copper wire near a compass needle, the needle moved in response. Unseen action at a distance wasn't a novel concept. Everyone knew about magnets, and a compass needle was magnetized after all. But a simple copper wire with an electric current flowing through it was not. And so its magnet-like effect on the compass was a sensational new experimental proof of the connection between electricity and magnetism. But no one really knew what to do with the revelation until a 20-year-old former bookbinder, who happened now to be working as Humphrey Davy's assistant, saw how it could be used to build an electric motor. His name was Michael Faraday, and he was absolutely an experimental genius. When Faraday saw that an electrified wire caused a compass needle to move, his first impulse was to organize the wire and the compass spatially to make it easier to observe the precise direction of the invisible force emanating from the wire. So he aligned the charged wire vertically to run straight up from a tabletop and then encircled its base with several compasses. When he did this, the path of the force became crystal clear. All of the compass needles pointed at a right angle to the wire, forming a circle, needle to needle, around it. This was incredible, for it showed Faraday that an electric current actually exerted a force field that flowed around it. And to demonstrate this to his amazed colleagues, Faraday replaced all the compasses, which were just little weak magnets anyway, with a single stationary magnet, a larger one, and dangled a charged wire near it. The wire began to rotate on its own around the magnet, carried along by the electromagnetic force field. The year was 1821, and this was the world's first electric motor, the modest assembly of a 20-year-old assistant who, like his boss Humphrey Davy had done with the arc light in 1808, was showing the world that electricity might power a radically different future. Over the next decade, Faraday carried on with his electromagnetic experiments, and in 1831, he completed his true masterpiece. That year, he built a machine that reversed the electromagnetic effect. Instead of making an electrified wire move in the presence of a magnet, Faraday produced an electric current in a coil of wire by moving a magnet through it. This was induction, the basic principle of all electric generators that would go on to power the modern age. Now, anyone could rig up a steam engine to move magnets around a mass of conducting material, like a spool of copper wire, to generate vast amounts of continuous electric current. And not surprisingly, enterprising inventors started capitalizing on electromagnetic induction almost immediately. The first was Samuel Morse, who led the development of long-distance telegraph communication in the 1840s. His system simply took advantage of Faraday's discovery that electromagnetic induction could go both ways. You could either use a magnet to make electricity or use electricity to make a magnet. The telegraph featured the latter. Every time a telegraph operator pushed down on his sending button, he closed an electric circuit, sending a current flowing through wires hundreds or even thousands of miles away into a coil of copper wire wrapped around a small bar of iron at the receiving end. This magnetized the bar of iron, causing it to tap against another piece of metal placed alongside, to which it became suddenly attracted. A sequence of quick or long taps on the sending button, dots or dashes as they were called, would therefore be replicated by the receiving bar as it tapped against a metal plate with its intermittently induced magnetization, and then be decoded into a telegram by the receiving telegraph operator. In the 1870s, Alexander Graham Bell took a major step beyond Morse's transmission of singular dot and dash electrical pulses to send the full sound of a human voice through electromagnetism. His invention of the telephone was more a product of excruciatingly delicate engineering than anything else. Bell had to minutely calibrate the faint vibrations produced on a paper diaphragm by the sound waves of speech with a corresponding output of undulating electric current. The undulating current would, in theory, travel through a wire and reproduce the same physical motion of the sending diaphragm in a sensitive electromagnet on the receiving side of the circuit, whose induced movements would vibrate a second diaphragm in a speaker at the receiving end in exactly the same way, vibrating the air at exactly the same frequency, which would be heard by the human ear as a replication of the spoken voice. After years of working at this, Bell succeeded in 1876, proving that the physical movements of an electromagnet induced by electric currents could be extremely fine indeed, fine enough to move in a fixed diaphragm according to the minute frequency variations of human speech, music, or any other sound.
Alessandro Volta.
Of course, the most famous inventor to leverage Faraday's discoveries was Thomas Edison, and his most famous invention was the electric light bulb. It had been nearly 300 years since William Gilbert published his book by the time Edison was manufacturing his first viable light bulbs in the 1880s, and the world was changing fast now under the influence of instantaneous electrical communication and lighting. And yet, what electricity actually was still remained a complete mystery. Edison infamously tested hundreds of different filament materials for his bulbs, from human hair to bamboo, before arriving at a thin strand of carbon because he didn't know what was happening at the atomic level in a current-supporting filament. While it had become clear that the flow of electric current would heat some materials white hot, like his carbon filament, while leaving other materials relatively unchanged, like copper wire, the reason why remained elusive. People like Edison were simply clever and tenacious enough to build the electrical systems of the modern world without truly understanding the nature of the force that made them work. In fact, Edison's ignorance enabled a rival physicist with more accurate theories about electrical science to surpass him in building out the nation's electric power grid. While Edison built numerous devices to take advantage of available electricity, a Serbian immigrant named Nikola Tesla deserves all the credit for designing a practical system to deliver it. By the end of our time traveler's own century, the world would have already looked fantastical to him, filling up as it was with electric appliances like fans and pumps, electronic communications like telegraphs and telephones, electric lighting that made the night as bright as the day, and even rapid electric transportation systems like subways and trolleys. The technology of electricity had far outpaced the science of electricity. But for technological progress to continue accelerating, that would need to change, which required the very nature of matter itself to be better understood. Since the 1860s, mathematics had suggested that one of the key features of electromagnetic force fields was that they actually radiated through space like a series of waves. But it wasn't until the 1880s, around the time that Edison began making light bulbs, that scientists succeeded in demonstrating this experimentally. And it was this that proved critical to finally understanding what electricity actually was. In 1887, a German physicist named Heinrich Hertz set up an electric generator to emit strong sparks on one side of a room and a simple circle of wire with a tiny gap in it on the other side of the room, unattached to anything, just sitting there by itself. And after looking through a sort of microscope at that tiny gap, he was able to see minute sparks jumping across it every time a strong spark cracked on the far side of the room. The presence of that tiny spark proved both that electromagnetic energy did radiate across space and that it could be received intelligibly. This was the first step in wireless communications. And as an experimental seed of technology, it looked like another gold mine. Sure enough, inventors fell over themselves to patent the first generation of wireless telegraph technology. But for wireless communications to replicate the earlier wired evolution from telegraphs to telephones, the reception of electromagnetic radiation, soon called radio waves, had to be vastly improved, for as they propagated out through space from their source, the strength of radio waves decreased significantly, like ripples on water thinning as they spread. To amplify the reception of radio waves' faint signal at a distance, scientists built an ingenious device called a vacuum tube amplifier. On one of its ends, the vacuum tube received the faint patterns of electrical current corresponding to a radio wave signal, just like Hertz's circle of wire did. And as that current then flowed through the tube, its signal was amplified by an electric field that functioned similar to the way a magnet attracts iron filings, pulling the electric current into faster velocity. By the time the undulating signal of electric current collided with the other side of the vacuum tube at its much increased velocity or signal strength, the amplification had made it much clearer. Clear enough, in fact, to be able to induce the same principle of electromagnetic vibration in a receiving speaker diaphragm that Alexander Graham Bell had used in his telephone. This is what made wireless broadcast possible. But this is also where the vacuum tube helped reveal what electricity really was. Because the electric current flowed through a vacuum, the only thing that affected it was the electric field, providing a pure and isolated influence that could be studied precisely. According to the specific way in which the electric field changed the velocity of the electric current, scientists were able to calculate both the charge and the mass of the particles composing it. They discovered that these particles were negatively charged and extremely light, and they named them electrons. Electrons flowed as a current in relation to much heavier, positively charged particles that were named protons. It was just about 1900. After 3 centuries of work, we finally knew what electricity was made of. Our time traveler looks a little stunned at this point as his gaze falls back to the glowing face of the smartphone in his hand. He tries to visualize the tiny electrons propelled through its circuits by a battery that must be far more advanced than the Voltaic Pile invented during his own lifetime. There is still so much about the technology that he does not understand, but he has come to understand it as a technology rather than as the magic of some supernatural power. It is humanity's cleverness that now dazzles him most. Subtly, he begins to shake his head as a wide smile slowly spreads across his face. He has so many new questions he wants to ask. Time for another little service announcement. I love doing these podcasts, and if things go my way, I'll continue to be your own personal history professor for years to come. However, it's still quite early in this little venture of ours, and I need all the help I can get to spread the word about how it began. So if you like what I'm up to here, please take a moment and review the show on iTunes or wherever you happen to listen. Or perhaps you could post something about it on Facebook, Twitter, or Reddit. By all means, blog about it. And let's certainly not forget the all-powerful word of mouth. How It Began is starting to gain traction thanks to those of you who have already done one or another of these things. You know who you are, you studs. So let's keep it rolling. For more information on this episode, including a select bibliography, visit howitbegan.com. I'm Brad Harris. So long.